All right, welcome back, class. Congratulations, we're progressing our way through. You all have just finished your first midterm. That marks about the 40% mark or so. We've covered a lot of territory over the last 11 lectures leading up to this point, where you've learned the fundamental postulate of stat mech, some basic definitions, how it connects to thermodynamics. And now we're in the midst of a discussion about how we actually utilize the formalism of statistical mechanics, and specifically the computation of partition functions, to give us insight into specific systems that we're interested in. We focused a lot on classical independent particle systems thus far, progressing through simple models of solids or lattice vibrations in solids, as well as simple gases. And we've made a lot of use out of a specific property of non-interacting systems, which is that their partition function factorizes into a product of single particle partition functions and then some factor that accounts for indistinguishability. So today, after we briefly review those results, we're going to reconsider this notion of indistinguishability and confront the fact that you all know that reality is described by quantum mechanics, and quantum mechanically, particles are not indistinguishable. And so how do we reconcile that these indistinguishable assertions we've made classically do end up yielding results which are consistent with our everyday experience? So we'll confront directly in distinguishability, quantum mechanically, not just assert it from this permutation factor, and then see how it arises as just that simple overcounting factor. All right, but to review where we've come, so we've considered a number of different systems that we would call non-interacting. The hallmark of a non-interacting system is that its energy can be written down as a sum of the energy of particle 1 plus the energy of particle 2 all the way up to the energy of particle n, where that energy of particle 1 only depends on the internal states of particle 1, not what particle is doing in addition. For such systems, the partition function factorizes into what we've called little q to the n, where this little q is what we've called the single particle partition function. That is the number of thermally accessible states for that individual particle. Now, if those particles were particles of a gas or phonons in a solid, the factor that makes this an equality in factorial is accounting for the indistinguishability of those individual particles. So I can't physically label the particles in my gas so that I can keep track of their unique state. What I can do is measure the aggregate state of the system, in which case I don't distinguish one particle zooming around one part of my box from statistically another particle zooming around in that box. We have utilized this factorization of the partition function for a general classical single particle. So that single particle partition function in a classical system can always be written as, that's a little funky of a Q, let me try that again, as an integral over where the particle can be. Let's imagine this is in one dimension, an integral over how fast it's going. And then a Boltzmann factor associated with momentum fluctuations, and in principle, some potential that depends on where it is. And we've argued that we can count those states with some resolution, where that resolution is something we had to introduce artificially. We imagine that there's some little box, delta P in height and delta X in width, from which we can count an individual microstate of the system. We've noted that quantum mechanics gives us some information for how that might be chosen, namely that delta X times delta P should maybe be Planck's constant. And we've also considered a significant amount the fact that this integral here, integral over the momentum, is something that can be done independently of any integral over position. Then that's a Gaussian integral, so we know how to do that. And when we do that, putting this all together, one can rewrite the single particle partition function as an integral over where the particle can be, weighted by the potential part of its Boltzmann factor, measured in units of this lambda of t, the so-called thermal wavelength. It is, in effect, the resolution with which we can count spatial patterns for a classical system. It's given by employing that factor of Planck's constant for the resolution delta X delta P, and the result of that Gaussian integral, which gives us 2 pi m times kBt square root of. Indeed, that has units of length, canceling out the units of length in the integral over dx. Now that's a classical single particle partition function, h bar entering in only through a correspondence by which we say that we will arbitrarily choose that delta X delta P resolution to be consistent with quantum mechanical results in the appropriate limit. And we have seen that that appropriate limit is when the energy spacings that are discrete quantum mechanically are small relative to kBt, the thermal energy scale. So another way to say that is that quantum mechanical effects are important if kBt is on the same scale as some discretization in the energy levels. Something like so. And also it's important if there are few excited states, so that kBt, such that the temperature doesn't distribute amongst many of those states, blurring out the effect of discreteness that actually underlies it. Okay. So that's kind of where we've been. We have a general procedure for taking a non-interacting set of particles computing their single particle partition functions, finding this factorization. Classical systems, with respect to their momentum, we can always handle. That always, when integrated, gives us this effective resolution with which to count spatial states in. And in some cases, we can do that integral over the potential part of the Boltzmann distribution. For example, if the system is a harmonic system, or if it's a constant, probably you even do that integral if it's a linear potential. But other than that, it's going to be probably pretty difficult to actually compute that potential contribution to the partition function. And quantum mechanically, we know that it will be acceptable to proceed classically as long as we're in the limit where kBt is large relative to some fundamental gap in the system, some energy spacing with which that discreteness is clear. Okay, but so far we've talked about discrete levels from the perspective of only one particle occupying them. What if we actually have a system of n particles quantum mechanically? This is the question or the system we'll address today. So thus far, just rephrasing it, we've imagined a single particle, say a harmonic oscillator or a free particle whose Schrodinger equation we can solve, giving rise to some set of discrete energy levels. Those discrete energy levels then, only one of which is ever instantaneously occupied. A single particle is only ever in one energy eigenstate at equilibrium instantaneously. It might transition between multiple energy eigenstates over the course of thermal fluctuations, but it's never in more than one. There's only one particle to occupy that state. So what if we now consider explicitly n particles filling the same set of energy levels? So being explicit, we could imagine solving some many particle Schrodinger equation, getting some set of energy levels, say epsilon naught, epsilon 1, this one has energy epsilon 2, and it would continue on. And I could imagine then particles, say 1 and 2, filling that lowest energy state. Maybe particle 3 fills the second lowest state, etc. So how would I distribute my n particles amongst these energy levels? Well, to think about the statistics of such a system, we first should make concrete how we describe that instantaneous state of the system. So what is the microstate of the system? And a simple way to denote that microstate would be to denote the occupation of each energy level. Say how many particles are in energy level 0, how many particles are in energy level 1, up to however many energy levels there are. In principle, these numbers could be any integer, 0 through infinity. And again, this N0, for example, would denote the number of particles in the 0th level, for example. That's a convenient way to denote the state because the energy instantaneously of the system is then easily computable from that microstate as summing over all energy levels, the energy of that level times its occupation. So in this diagram here, I have 2 particles in ground state 0, so I'd have 2 epsilon naught plus 1 epsilon 1. With the microstate and energy defined, we could now ask the question, what's Q, the canonical partition function? Now, immediately there's a couple complications with actually going forward with this calculation. Do you see it? So Q is a sum over microstates. We've denoted the microstate. I need to sum over all the possible values N0 can take, all the possible values N1 can take, up to however many energy levels I have. I have a Boltzmann factor. You know, it still has this nice linear structure, but it's deceptive in this case because we have to remember that Q is a natural function of T, V, and N. The canonical partition functions envisions a system where the particle number is fixed. That requires, if N is fixed, that the sum over all of those occupation variables equals N. There's a constraint. There's a constraint that then couples all of these sums. Sorry about that. I can't do the N0 sum independently from the N1 sum because if I set the particle number in my system to be 2, for example, well, N0 can be 1 or 2, but if N0 is 2, N1 has to be 0. That's not a huge complication to overcome. There's a simple solution. If it's difficult to work when N is fixed, well, let's just not fix N. We can work in the grand canonical ensemble. Everyone remember what the grand canonical ensemble means? That's fixed temperature, so the energy can exchange, volume, and instead of N, it fixes the chemical potential, which means that N can fluctuate. This capital C, still a sum over all occupancies. That's still the microstate of the system. And now instead of weighting by solely the sum over the energy level, the energy of the ith energy level times its occupation number, I now have to additionally add a term, beta mu, times the total number of particles in the system, which is easy, also expressed as just a sum over N, the occupation level of each level, the occupation number of each level, excuse me. So that's the first complication and its solution. The second is a little more subtle, and you might have occurred to you even just in how I drew this diagram. You all, or many of you, are chemists and have some appreciation for the fact that I can't just arbitrarily decide how many particles are going to occupy a given level. There might, in fact, be restrictions on what values of Ni can be. Now, those are details that depend fundamentally on quantum mechanical aspects of the system. So to understand first how those restrictions come about and how to handle them with respect to the computation of the partition function, we need to take a little bit of a detour and remind ourselves about different kinds of particles that exist quantum mechanically. Okay, so let's remind ourselves about some basic facts of quantum mechanics. Let's imagine I can construct an operator P to permute particle indices. So let P be the permutation operator. What does that mean? Well, let's imagine I have some set of particles in orbitals centered at different positions, say Ri and Rj. The action of this operator will be to switch those labels. Like so. Now, the physical system does not care about how I decide to label particles, which means that that permutation operator, when I swap those labels, I don't change the energy of the system, which must mean that the permutation operator and the Hamiltonian, the energy function of the system, that they commute. That's just a mathematical way of saying that the energy is independent of particle labels. So being a little more precise, if I imagine acting that permutation operator on a wave function, again, it's a many body wave function. It has information about where some number of particles are. Acting that on a wave function in general will satisfy its own eigenvalue equation. So acting P on some wave function will generate an eigenvalue little p and enforce its action on a state, which is then to switch labels, like so. If I act that operator twice on a state, well, I can do that by acting on it once, giving me that top line, and then again, it gives me another factor of p, so I have something p squared, and I have to return back. If I swapped I for j the first time, I swapped j for I the second time. So two actions of the permutation operator give me back my original state. So that implies that this eigenvalue, the eigenvalue associated with operations of this permutation operator on some wave function of a system, must take specific values. For those states to be the same, it must be that p squared is equal to 1. Which means that the possible eigenvalues associated with the permutation operator are plus or minus 1. Now this is a fairly simple exercise. It's a symmetry associated with a wave function, permutation symmetry, which a wave function either has, in which case p is 1, or it doesn't, in which case the wave function is anti-symmetric with respect to permutations, and this p is minus 1. As simple as that is, that breaks our world into two fundamentally different types of quantum mechanical particles. I think you all are expecting what those things are called. We'll name them in just a second. In fact, I don't know if you all are avid archive readers like I am. If you are, you might actually know that there are more than two fundamental types of particles, but we will only consider two. To understand how that impacts systems and what the implications are before we name those two different types, let's consider a Hamiltonian, which is a sum of single particle operators. Labeling the indices of all the particles with this alpha. So this is an example of a non-interacting system, quantum mechanically. Generalizing the notation we've used before, this is a Hamiltonian operator, which is a linear sum of single particle operators. That means that the differential equation, which, the Schrodinger equation for the system, is linearly independent. I can solve each one of those individual particle problems separately. It's a separable differential equation. It would lead to something like this: an individual particle Hamiltonian acting on some eigenvector, returning some energy and that eigenvector back. So diagonalizing that single particle operator is done through the solution of a single particle Schrodinger equation, like so, in which case there are, in general, a number of potential solutions. I'll index those solutions with these J's here. So if this is the solution to that Schrodinger equation, but I have a mini particle system, that means that in order to solve the mini particle system, I need to take superpositions of these single particle states. So let's see how this plays out for a case where just n is equal to 2. One could imagine that the total wave function of the system, depending on R1 and R2, could just be, for example, a product of these single particle functions, say phi I for particle 1 and phi j for particle 2. Maybe that is a potential state that would then be a solution of the mini particle Hamiltonian. But This wave function, a simple product, does not satisfy that permutation symmetry that we've elucidated already. If we act P on that wave function, I don't get that wave function back again. I don't get a simple eigenvalue of plus or minus 1 back. So the simplest symmetry allowed function would be a linear combination of that product state. So for example, for P is equal to 1, a potential wave function that satisfies our permutation symmetry operator, which again, because it commutes with the Hamiltonian, shares a set of eigenfunctions with the Hamiltonian. So these are these are statements of the energy eigenfunctions of our many-particle Hamiltonian. For P is equal to 1, the simplest possible linear combination I could imagine for two particles would be a product of phi 1 at R1, phi j of R2, plus now phi I at R2, phi j at R1. Indeed, if I switch those indices, I'm left with a wave function which is symmetric under that permutation. So P1 is a classification of wave functions which are permutation symmetric. For P minus 1, therefore, I can construct a many-body wave function as an anti-symmetric linear combination, whereby I have phi I R1 times phi j at R2, now minus phi I at R2, phi j at R1. Acting our permutation operator, switching the particle indices, indeed, in this case, results in a overall negative sign from the original wave function. Now note, there's just a minus sign between the permutation symmetric and permutation asymmetric, anti-symmetric wave function. And yet there's a profound implication for the anti-symmetric wave function. Setting I is equal to j doesn't make any sense. Because that would mean that the overall wave function is 0. Now, I and j are just labels for the eigenvalue of the single particle levels. So this implies a constraint on the occupation of those levels. So now let's go ahead and name these two different fundamental types of particles. When there is a constraint, we call those fermions. The occupancy can only be 0 or 1. Either state is unoccupied or it's occupied by a single fermion. So that's the permutation antisymmetric wave functions. The type of particle which has no restriction on its occupation, so the occupation could be 0, 1, all the way to infinity. Those are the class of wave functions which are permutation symmetric. Those are what we call bosons. Now, I alluded to the archive. I don't know if there's any condensed matter people in the audience, but there has been for a long time postulates that one could have a third class of particles, so-called anyons, whereby that P eigenvalue is not just integer 1 or -1, but has some complex phase that rotates between 1 and -1. Indeed, anyons have been observed in condensed matter systems somewhat recently. But that's new, we won't talk about it here. We will, however, understand the implications of this constraint for statistical fluctuations. So in fact, very early on, kind of in the second wave of quantum mechanical results, people like Fermi and Dirac, Bose and Einstein started thinking about the implications of these occupancy constraints on observable properties of groups of fermions or bosons. So let's work through some of those consequences now. So the first thing we'll consider are so-called Fermi-Dirac statistics. Those are the statistics of fermions, where occupations are 0 or 1. Fermi and Dirac discovered this fundamental distinction about the same time. That's why they both have their name. Though Fermi published the paper first, Dirac was not a big literature reader, so he discovered it independently. So for Fermi-Dirac statistics, our partition function, which is a sum over all the occupation numbers possible for all the potential levels. In the grand canonical ensemble, this is then going to be weighted by a Boltzmann factor, indexes the energy level with I, and now we can bring in those two sums together, so we have the energy of that ith level less that its chemical potential times that occupation number. Now, that exponential is a sum, which means that it factorizes. I can consider a product of exponentials, each one of them indexed uniquely to its own energy level. So this partition function, again, takes on a product structure, a product over the I energy levels, and a sum, if these are Fermi-Dirac statistics, of the ith energy level being either 0 or 1, weighted by this Boltzmann factor. And now this is no longer, the term in here is no longer a single particle partition function, but is nevertheless an individual partition function. We would call this the single level partition function. And let's denote it z of I. It's the ith level partition function. It is something we can compute. There's only two terms in that sum, where n is 0 and where n is 1. So summing those two, we have when n is 0, we have a factor of 1. And when n is 1, we have an e to the minus beta, the energy of that level shifted by the chemical potential. So now we can ask questions. We've computed the partition function. each level has an identical form to that partition function, just changes what we mean by its energy. So all of our results that will follow will be analogous for any level. But for the ith level, we could, for example, ask, what is the average occupation of that level? I could choose a level within my manifold and ask, how likely is it that a particle occupies that state? So let's denote that average in I. I can compute that by taking a derivative of that single particle partition function with respect to beta mu, holding the temperature and volume fixed. I could see that that will generate that average occupancy because beta mu is upstairs in the exponential conjugate or multiplying ni. So if I take a derivative with respect to beta mu, I will pull down a factor of ni. Taking that derivative, d log z with respect to beta mu, I get a factor of e to the minus beta, the energy of that ith state, less than its chemical potential, less that its chemical potential, over 1 plus that same factor. Rewriting by multiplying top and bottom by e to the plus beta, the energy less its chemical potential, I have 1 plus e to the plus beta, the energy level less its chemical potential, all inverted. That function is the so-called Fermi function. At high T, for example, as temperature goes to infinity, what does that go to? So if temperature goes to infinity, E beta goes to 0, 1 plus a very small number just becomes 1. So I will go to something that looks like just e to the minus beta EI less than that chemical potential, as long as mu is less than EI. If we were to plot what this average occupancy looks like, say as a function of the energy of that level, well, where does it start? So at very low energy, that level is occupied with unit probability. At very high energy, that level is unoccupied. Say if we put mu here, so that's relative to that chemical potential. At exactly mu, we have E minus mu is 0. We have up top e to the 0 over 1 plus e to the 0. That's 1/2. So it's exactly at the chemical potential. We have 1/2. And it interpolates something like so. How quickly it goes between 1 and 0, however, depends on the temperature. So at low temperatures, it's very sharp. At high temperatures, it's very broad. That width is essentially kBT. So that's the average occupation of some level. What about the fluctuations in the occupation? So delta n squared, which is equal to average of n squared less average of n quantity squared. Now there's a simplification when n is a binary variable. if n can only take values instantaneously of 0 or 1, which is true for our fermions, then every time n is 1, I square it, I get 1 back. Every time n is 0, I square it, I get n back. So in fact, the average of n squared is the same thing as the average of n, which means that the fluctuations are just the average of n times 1 minus the average of n. Again, that is inherited because n squared equals n when n is 0 or 1. So in fact, this is by just knowing the average occupation, we also already know the fluctuations in that occupation. Fluctuations we can already see will only occur, therefore, when n is not close to 1 or close to 0. If n is 0, those fluctuations go to 0. If n is 1, they also go to 0. Okay. We can do something kind of fun, given we've just computed the partition function, which is to remind ourselves that that partition function, the grand canonical partition function, has a thermodynamic meaning. It is equal to the pressure. So we can then ask, what is the pressure of a box of fermions? Reminding ourselves that beta PV is equal to log capital C, our partition function. When we computed that partition function, we had a product over the ith levels, the single level partition function, filling in that single level partition function and noting that the log of a product is the sum of the logs. There we have it. That's the single level, the ith level partition function. Now, we noted that as beta goes to 0, or as t goes to infinity, this factor here so if beta goes to 0, that exponential is a small number. The log of 1 plus a small number is that small number. So I'll get a sum over just those Boltzmann factors for the ith level. This is approximately equal to that average occupancy in that high temperature limit. That follows from what we said here. The average occupancy in the limit that the temperature goes large is just reduced to that Boltzmann factor. So what we've just learned, putting that together, is that beta PV is equal to a sum in the high temperature limit of the average occupancy of each level summed over each level. If I sum over each level the average occupancy, that's the same as knowing the average total number of particles in the system. Okay, now this, I'm really a one-trick pony. You all will then recognize this as the ideal gas law again. So even a box of fermions in the high temperature limit, which are non-interacting in the high temperature limit, obey ideal gas. The ideal gas law have uncorrelated density fluctuations. But we can actually do something more interesting for the fermions, which is hard to do otherwise. We can ask what happens at low temperature. So at low t, that's like saying beta goes to infinity. If mu is greater than epsilon I, so that the level is filled, then what have we found? So if in the case that mu is greater than I, EI, so as beta gets infinitely big, so let's work this out again. So we have beta PV is a sum over each level, 1 plus e to the, I'm going to rewrite this as mu minus EI, so take out that minus sign. So if mu is greater than EI, that's a positive number in that exponential. As I take beta to infinity, I get something that diverges. I get something that gets really big under the log and then still gets big. This is something that goes then to infinity. So what does that mean? If I start trying to fill more and more levels at low temperature, the system becomes, the pressure gets infinitely big, the compressibility gets infinite. At low temperature, a box of fermions is completely incompressible. But there's no size to the particles. We haven't said what those single particle Hamiltonians look like. These could be plane wave states. These could be just particles with kinetic energy. So what is resulting in an effective incompressibility? It's not that they have size, but in fact that they, as I start going to lower temperature, what's going to happen? Those electrons are going to pile up in the lowest energy levels, and I can't do anything more than that. If I try to rearrange those particles at really low temperature, they will only occupy those lowest energy levels. Essentially, this is a manifestation then of the Pauli exclusion principle. All right, that's a bit of an aside. Now let's consider the other class of particles, so-called bosons, that exhibit what is known as Bose-Einstein statistics. So those are particles that have permutation symmetric wave functions that have no restriction on the occupancy level, on the occupancy number of an individual energy level. So the grand canonical partition function can analogously be written down as a product over single level partition functions, just as we saw in the fermion case. But now what that single energy level partition function means is now a sum over the occupancy of that level being 0 to infinity. If I write down the associated Boltzmann factor, I could rewrite it in a telling way. Now, what does that look like? I sum from 0 to infinity, some number raised to that index. That's another geometric series, just as we saw before, which is one we can do, and we get 1 over 1 minus e to the minus beta epsilon less the chemical potential. Where did we see that before? Harmonic oscillators. harmonic oscillators, phonons, vibrations, those are in fact bosons. There's no restriction on the excitations in a given vibrational state. So this is not surprising. Are there any restrictions for doing that geometric series? Can anyone think of a case where that series would not converge to something simple? All right, hold that in your mind. So we can play the same sort of game with our bosons. We can compute the average occupancy by a log of that level's partition function. Doing that in this case, where you get a 1 over e to the beta, the energy of that level, less the chemical potential, now minus 1. Now that looks a whole lot like our Fermi distribution. The only difference between that Fermi function and this function, the Bose-Einstein distribution, is that here we have a minus 1, while the Fermi distribution is a plus 1. But that is a huge difference. Let's see what that looks like when we plot it. So if we plot average n as a function of, say, mu, so for small mu relative to the energy level, so that means that, so when mu is less than that energy level, that whole factor in the argument of the exponential is positive, but I have 1 over that factor, so that gives me something which is small, so it's going to start at 0, and it's going to increase. Now what happens when epsilon I is equal to mu? Well, e to the 0 is 1. 1 minus 1 is 0. When I have that in the denominator, that diverges. And again, the scale, how rapidly it diverges, depends on the temperature. So at low temperature, it will be 0 until it diverges. That's crazy. We get an infinite number of particles occupying a given state. This is known as a phase transition, and the specific phase transition is so-called Bose-Einstein condensation. I can collapse in a macroscopic number of particles in a given level. This underpins everything from superfluidity and superconductivity to a whole host of other electronic and materials phenomena. And it's one of the only instances from which a singular behavior can arise in such a simple algebraic calculation. Okay, but even Bose, whether or not in bosons or fermions, at high enough temperature, we've argued that quantum mechanics shouldn't matter. So let's see if that still is true. One way to state this is that at high enough temperature, it shouldn't matter whether or not a particle is a boson or a fermion. I should get the same sort of result. So let's think about this by noting that the average particle number in this grand canonical calculation can be computed, as we did previously, as a sum over the average occupancies of the ith level. Putting in the functional form for that average occupancy, we can express both fermions and bosons compactly as a factor of the e to the beta, the energy of that level, less that the chemical potential, minus P inverse, where P is plus or minus 1, depending on it, the particles being fermions or bosons. Now let's take the limit of small n and high temperature. So high temperature is the same thing as beta going to 0, such that e to the beta epsilon minus mu is much, much greater than 1. So small n, therefore, means that the occupancy is very low. The only way to get a low occupancy is to have the chemical potential be a lot larger than the energy level. In that case, I have e to the minus beta times some factor, which is positive. As I take beta to 0, I have 1 over a factor which is getting small, which then is something which gets big. So in that case, the average occupancy, if that factor is very big, is big compared to P. So it will grow like e to the minus beta, the energy, less that the chemical potential. Now that is true irrespective of what P is, because in this case, this term is much, much larger than P, so I can neglect P, be it plus or minus. So if that's the case, average N is equal to a common factor for all the energy levels due to that chemical potential, which can be pulled out of the sum, leaving me with a sum over the energy levels, e to the minus beta, the energy of that level. Now, a way to compute the probability of having a particle in the ith level would be to ask for its average occupancy over the total average number of particles. From the two expressions on the left, so those two, the average ith level occupancy, e to the minus beta ei minus mu, over the average total occupancy. Well, the factors of mu will cancel. I'll be left with e to the minus beta, the energy of the ith level, over a sum of those factors for all ith levels. What does that look like? That is just our Boltzmann distribution back again. So irrespective of whether or not the system is described by Bose-Einstein statistics or Fermi-Dirac statistics, in the high temperature limit, in the limit that there are many levels occupied such that the density in any one level is really small, the probability of being in a specific energy level is just given by our usual old classical Boltzmann distribution. Now, how does that relate then to Q? Our canonical partition function. Well, log of Q is equal to log of our grand canonical partition function minus beta mu average of n. That's saying that's a statement of a thermodynamic relationship, that log of Q is minus beta times Helmholtz for energy, log of capital C, that's beta times pressure times volume, thermodynamically beta mu n. So thermodynamically, that average fluctuations are suppressed in a thermodynamically large system, so the average dominates the observed behavior. And so really what we're saying by this equality is indeed just saying that the energy is equal to Ts minus PV plus mu n. Reminding ourselves that the Helmholtz free energy is just E less than Ts. Okay. So if that's true, if there's a simple relationship between Q and C, those two partition functions, let's see what that implies. So log of Q is therefore equal to minus beta mu average of n plus, now what is the log of our C? Log of that partition function, we had that there a second ago. Where was that? So log of that partition function is going to be a sum over those energy levels, the ith level, times that single state partition function. So that's then a sum over the log of e to the minus beta mu energy of that level less that the chemical potential minus P, where again, P depends on whether or not this is a Bose distribution or a Fermi distribution. And I can write this all together if there's a P outside. No, sorry, I don't need that. Okay, so in the high temperature, or I can think of that whole sum of the log as summing over each ith level, e to the minus beta, energy of that level less that the chemical potential. That is, again, what we've just found in the high temperature limit to be the average number of particles. So rearranging all of this, I find that beta mu, so pulling the beta to one side, is log of average n less that log of the sum over each energy level, e to the minus beta, the Boltzmann factor for that level, and putting this together. So that is just manipulating that. So putting this together, we have log of Q is equal to quantity minus log average n plus log sum each energy level, Boltzmann factor of each level, all times average n plus average of n. So that's putting those two pieces together. Now let's consider what we've just found. So if I sum over each level, the Boltzmann factor for that level, this is really what I meant by my single particle partition function. Right, that's the normalization for a single particle that can exist in any energy level indexed by I. Now, when I take the log of that and multiply by average n in the thermodynamic limit, that's just like saying that that's log of q to the n. All right, that sounds interesting. So what about these other factors? So I have n log n minus n. That's Stirling's approximation. So actually, if I exponentiate both sides, I find that q is little q to the n over n factorial, if we're in this thermodynamic limit such that n is large and average n is n. So we've just uncovered, as we would have expected, that in the high temperature limit and the macroscopic limit, whether or not we're considering bosons or fermions, we get back the same sort of classical particle behavior we have been using thus far, to great effect. Okay, so what have we just done? So we've acknowledged that there's some complexity when we start thinking about indistinguishability quantum mechanically, and we introduce some machinery to consider both types of fundamentally indistinguishable particles, bosons or fermions. We've noted some of the properties of bosons and fermions that are different. Fermions, because they can only have 0 or 1 occupancy, have a Fermi distribution, a little smooth step function that tells us whether or not a given energy level is likely to be occupied, while bosons can exhibit Bose-Einstein condensation, whereby all the particles pile up into one energy level. So the permutation symmetry of the wave function has macroscopic consequences when we start thinking about collections of particles. When we go to a classical limit, high temperature, low occupation probability, low density, those details completely wash out, and we arrive at something that behaves classically and independent of whether or not the individual particles are bosons or fermions. So we'll use this machinery next time to consider a case of non-interacting electrons. This will help us understand how metals behave, simple models of metals behave. So stay tuned for that. And again, just a quick note. So I've glanced over your midterms. By eye, they all look like you all did very well. So I'm very pleased with all of your efforts there. Suggests to me that you are all following. So I think that's great. All right. So hopefully I'll see you on the live session on Tuesday.